Well, we're going to talk today about sections 3.1 and 3.2. Yes, it's two sections, but also it's stuff that I think you've probably seen before. So that doesn't mean you don't need to pay attention, but it means that, you know, it's not like the day when we did the product rule, the quotient rule, and the chain rule all at once. Okay, we're going to learn about exponential functions, their properties, also their inverse, which is the logarithmic functions, and in particular, one very special exponential function and a very special logarithmic function. Okay, so you know that I care about building up things from certain basic concepts. And the exponential functions are something that has to be constructed from exponentiation as we know it in a familiar way. So what does it mean when we talk about raising a number a to a power x when x is any real number at all? Well, for certain numbers, we understand what this means. And then we have properties from which we can derive other relations. So the basic idea is that if you have a positive, or any real number, a, and you raise it to a power n, where n is a positive whole number, such as 3, 6, 12, whatever, then a to the n means write down n a's and multiply them all together. So a to the third means write down 3 a's and multiply them together, right? Or 3 to the fourth means write down 4 3's, multiply them all together. Negative 1 to the fifth means write down 5 negative 1's, not negative 1 5's, 5 negative 1's, and multiply them all together. That would be a result of negative 1. Okay, so this idea about what exponentiation means is very intuitive, very concrete. Now, what would that mean, though, if you wanted to take a number to the 1/2 power? Say 3 to the 1/2. Do I write down half of 3? Or 3 to the 0? How do I write down 0 3's and multiply them all together? Okay, so this analogy doesn't make sense for powers which are not positive whole numbers. Okay, but one thing we can tell, I should say this, when we're talking about the number a to the b, this whole expression is called a power, and the number a is called the base, and the number b is called the exponent. So sometimes I confuse power, which is the whole thing, and exponent, which is the actual superscript. But if I'm saying exponent, then I really do mean the thing up here, and the base is the thing at the bottom. Okay. So these are some basic properties of exponentials that are true, observedly so, when x and y are actual whole numbers. So the first fact is that if I take a to the power x plus y, that's the same as taking a to the x times a to the y. So a to the 5 is 2 plus 3, that would be the same thing as taking a squared times a cubed. And formally speaking, what it means is that taking a number to a power converts sums into products. Exponentiation converts sums into products. Exponentiation converts differences into quotients. A to the power x minus y equals a to the x divided by a to the y. Think about it with x equals 5 and y equals 2. Right? Take a to the fifth divided by a squared. That's the same thing as a cubed, which is a to the 5 minus 2. If I take repeated exponents, such as a squared and that to the cubed, then that's the same thing as taking a to the product of 2 times 3. A times b to the power x is the same as a to the x times b to the x. So you can distribute the power across the base when you're multiplying bases. So the power of a product of two numbers is the product of the powers of those two numbers. And all of that works just by writing down the left-hand side and the right-hand side and comparing them. If you're going to take a to the x plus y power, well, x and y are both positive whole numbers, so x plus y is a positive whole number. So you just write down that many a's, however many you have. And if you're writing down x plus y of them, then what did you do? First you wrote down x of them, and then you wrote down y more. So group the first x together, that's a to the x, and the second y together, that's a to the y. The product then will be a to the x times a to the y. And all the rest of those properties go through the same way because we're only talking about x and y being positive whole numbers. Okay, so that much is makes sense with our idea of repeated multiplication. Okay. Other powers we will be able to understand by the philosophy that we want these laws to remain true. We would still want to be able to say that a to the x plus y is a to the x times a to the y, even when x and y are not necessarily positive whole numbers. Okay, so that's going to guide our definitions for these other powers. For instance, what should a to the 0 be? Now, forget about the fact that somebody told you what the answer to that question is. How did the first person to come up with this idea come up with it? The idea is that you want to be able to say that a to the n, after all, n is equal to a to the n plus 0, that should be equal to a to the n times a to the 0. I put this little exclamation point here. That's my notation. It's not standard notation, just to say that this is an equation that we want to be true. And we would like to say that a to the n is equal to a to the n times a to the 0. We don't know what a to the 0 is, but what should it be if this equation has any hope of being true? 1, right? So we would say that a to the 0 is 1 in order for this equation to be true. All right? Now, this doesn't work if a is actually 0, because then this side is 0, and this is also 0, and you can't say that a to the 0 is 0 to the, you can't say that 0 to the 0 is 0 to the n divided by 0 to the n, and therefore 1, because that would be 0 divided by 0, which is not defined. So as long as a is not 0, we can say that a to the 0 is 1. Okay? And this is not one of the 10 commandments or anything. This is just a convention that we set up so that this rule can be true. Exponentiation converts sums into products. Okay. So 0 to 0 is still undefined. As a matter of fact, once we see limits where the base is going to 0 and the power is also going to 0, those will be indeterminate limits. So can we use the same philosophy to figure out what powers should be when the exponent is negative? Well, we just discovered what a to the 0 should be. It should be 1. So let's write 0 cleverly as n plus negative n. And if that's true, or if we can do that, then we could write a to the n plus negative n as a to the n times a to the negative n. And since we want that to be 1, we can solve for a to the minus n. It would be 1 over a to the n. All right, so then we can define, if n is a positive integer, such as 2, 3, or 4, a to the minus n, that is a to the negative 2, or negative 3, or negative 4, would be the reciprocal of that positive exponent power. So a to the minus 2 is 1 over a to the 2. A to the minus 3 is 1 over a to the 3. As a matter of fact, because taking the minus sign twice gets you back where you started, and because taking a reciprocal twice gets you back where you started, it's okay even to say that this equation is true when n is negative. Say n is negative 2, then a to the minus negative 2 would be a squared. And 1 over a to the minus 2 is 1 over a squared, which is also a squared. So this equation now becomes true even when n is a negative whole number. Okay, so a whole number which is either positive or negative is sometimes called an integer. So now we know how to write down a to the n when n is any integer, positive or negative. And then we can check for division that it still works nice and fine. A to the m minus n is a to the m divided by a to the n. Okay, so that handles exponents which are negative, and 0 we already covered. How about fractional exponents? Well, any fractional exponent can be written as a quotient of two integers, such as p divided by q. And just to keep things simple, we'll first start with a numerator of 1. So what should a to the 1 over q be? Well, if we remember this guiding principle that repeated powers are the same as multiplying exponents, a to the 1 over q to the q power, that should be the same as a to the 1 over q times q. That is a to the 1, and a to the 1 is definitely a. Okay, so whatever a to the 1 over q is going to be, its qth power is going to be a. but we have a name for that kind of number, the number whose qth power is a. That number is the qth root of a. Okay, so we can define a to the 1 over q to be the qth root of a. And if we have a to the p over q, well, then we can take the qth root of a and then take it to the p power. Okay. Now, one thing we have to make sort of definite, and that's that we cannot take the square root of a negative number. So if q turns out to be even, then we need to require that a is not negative. And as a matter of fact, many times we'll assume that a is going to be a positive number. Okay. So if q is positive and a is non-negative, a to the 1 over q is the qth root of a. A to the p over q can either be resolved as the qth root of a to the p or the pth power of the qth root of a. Either way you want to do it, you can do it. You get a to the p over q. So that allows us to write down what a unambiguous convention for a to a rational exponent. Okay? And that's almost everything there is, right? We have positive whole numbers, we have negative whole numbers, we have 0, and we have the rationals. But there are other numbers which are not rational numbers, even though they are real, such as the square root of 2. We don't yet know how to take a number a to an irrational power. What would 5 to the square root of 2 be? I definitely can't write down the square root of 2 5s and multiply them all together. And I can't use any of the relations that I was using before because I don't know how to write an equation that has as its solution a to an irrational power. Well, one thing we do know about irrational numbers is that they can be approximated by rational numbers. Right? And we do this all the time when we punch in these numbers into our calculator. When you hit pi on your calculator, you're not getting exactly pi. You're getting the calculator's best approximation to pi, which is still, after all, a decimal that ends. And so that's a rational number. So when we want to say a to the x, when x is not necessarily a rational number, we'll say that it's the limit of a to the r as r goes to x, taking only the rational ones. So find some rational numbers which get closer and closer to that number x. Take a to that power. That we know how to do because it's the pth power of the qth root of a. And then take the limit of those powers. All right. Now this is highfalutin language. Really what we do is we take better and better rational approximations to r and raise a to that power and see what these are going to. For instance, if we want to estimate 2 to the pi, well, let's think about estimates of pi. You know, to 1 digit, pi is 3. To 2 digits, pi is 3.1, 3.14, 3.141. These are all rational numbers. They can be written as fractions where the denominator is a power of 10. So you take the 314th power of 2 and then the 100th root of 2, and you would get something like 8.81524. Take a better approximation. That gives you a rational number with a larger numerator and denominator. Take that power, take that root. You get something which is, again, close to 8.8 something, something, something. So the calculator is going to tell you something like 8.82498, which we could get with pretty reasonable accuracy just by taking 4 decimal places or 4 digits from pi. Question? Sure. So this is the definition of a to the x as a limit, and this is how you might approximate a to the x if you knew a and you knew x. And here, the next slide has an example of that using a equals 2 and x equals pi. Okay? Other questions about this? So this is what's happening when this is the sort of the mathematical underpinnings behind exponentiation. All right. So let's talk a little bit about graphs of these exponential functions. The most boring exponential function is the function 1 to the x, which is that. Okay? If you write down n ones and multiply them together, of course you get 1. And if you take a reciprocal of 1, you get 1. If you take a root or a power of 1, you'll get 1. And so that's why 1 to the x is just 1. I guess 0 to the x is even more boring. It's just the function y equals 0, except it's not defined when x equals 0. Okay, so something more interesting would be 2 to the x. Here's the graph of 2 to the x. So the larger x gets, naturally, the larger 2 to the x gets. But what you'll find, which is really interesting, is that the function 2 to the x grows faster than x squared. It grows faster than x cubed. It grows faster than x to the 10th. It grows faster than x to the millionth. That is, for any polynomial function you want, you can go out far enough and find that 2 to the x is larger than that polynomial, no matter what its degree is. The exponential functions grow much, much faster than any polynomial function. Okay, so I didn't write any points on this graph, but you know that 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 4 is 16, and that's why we're off the scale already. Here's the graph of 3 to the x. As you can see, 3 to the x is larger than 2 to the x, because 3 is larger than 2, if x is positive. If x is negative, then what you're doing is comparing reciprocals. Right? 3 squared is bigger than 2 squared, but if you take reciprocals, the 1 over 3 squared is less than 1 over 2 squared. So that's why when x is negative, 3 to the x is going to be smaller. What's the limit as x goes to infinity of 3 to the x? Infinity, right? Just keeps getting bigger and bigger. What's the limit as x goes to negative infinity of 3 to the x? 0, because we're taking reciprocals of ever larger numbers, and so they're getting smaller and smaller. Okay, next I will graph 10 to the x. Where is 10 to the x going to fall in on this graph here? It's going to be here, here, yes, okay, so above 3 to the x, and here, here, here. Okay, you got it. 10 to the x is higher than, 10 is bigger than 3, so if x is positive, 10 to the x will be more. 10 to the x will be less than 3 to the x when x is negative. And so we could keep on doing that for any base we wanted. Let's look at a number between 1 and 2. Because the base is in between 1 and 2, then the power is also going to be in between 1 to the x and 2 to the x. So 1.5 to the x is this curve in between 1 and 2 to the x. All right, what if our power is negative? I'm sorry, what if our base is less than 1? Here's the graph of 1/2 to the x. Okay, at first it might be surprising that this ended up on the other side of the plane, right? That the large part ended up over here. But after all, if x is large, 1/2 to the power x is going to be a small number. Think about 1/2 to the 10. That's 1 over 2 to the 10, which is 1,000th, or thereabouts. That's a small number. If x is negative, we will take the reciprocal of 1/2, which is 2, and then raise it to a positive power, which is why we'll get a large thing. Okay. What graph on the right is this graph on the left related to? What graph of these is related to the graph of 1/2 to the x? The graph of 2 to the x, that's right. And what's the graphical relationship, the geometric relationship between 1/2 to the x and 2 to the x? They are exact mirror images of each other if you flip it over in the y-axis. And the reason for that is that 1/2 is 2 to the minus 1. So 1/2 to the x is the same as 2 to the negative x. So when you take a function and then plug in the opposite, you are reflecting across the y-axis. So the graph of 1/2 to the x is the flip of the graph of 2 to the x. And the graph of 1/3 to the x is the flip of the graph of 3 to the x. And here's 1/10 to the x, and 1 over 1.5 is 2/3 to the x. My labels are starting to run into each other. But as you can see, you get this whole family of curves. If the base is greater than 1, then a to the x will go to infinity as x goes to infinity, and 0 as x goes to minus infinity. If the base is less than 1, but greater than 0 still, then the function will go to 0 as x goes to infinity, and infinity as x goes to negative infinity. And what point do all of these go through? That's not labeled, but we can probably figure it out. What is it? That's the point 0, 1, because as long as the base is not 0, a to the 0 will be 1. So all of these curves go through the same point. Okay. And where do they not go? None of these curves go below the x-axis. A to the x, if a is a positive number, is always going to be positive. So when we think of the function a to the x, we restrict a to be positive, and it never becomes negative. Okay. Do you like my diagram? All right, very good. So let's talk a little bit more about these properties of exponential functions. All of these were carefully crafted to remain true by our conventions about what a to the 0 and a to the negative n and a to the p over q should be. Okay, so it's still going to be true that a to the x plus y is a to the x times a to the y, as long as a is any positive number, not 1. Okay, we'll get a continuous function whose domain is all real numbers and whose range is all positive numbers. If a is 1, then the range is not all positive numbers. The range is just 1. Okay, so any real numbers we have, a to the x plus y will still be a to the x times a to the y. A to the x minus y will be a to the x divided by a to the y. A to the x to the power y is the same as a to the power x times y. And then ab to the x is a to the x times b to the x. So all of these things were true, observedly so, for x and y being positive whole numbers. And then we carefully made sure they were still true by defining the other powers in a consistent way. So it's still true that exponentiation turns sums into products. It turns quotients, turns differences into quotients. It turns repeated powers into products, and it distributes across the base. Okay? So negative exponents, again, mean reciprocals. Fractional exponents mean take some root, and so on. Okay? So we did that for positive integer exponents, and then everything else we just sort of try to keep it true. And since we were able to do that, it's still going to be true. Okay. So let's get practical then. Let's think about simplifying a number like 8 to the 2/3 power. Okay. So there are two ways to think about 8 to the 2/3. One is that you can take 8 squared and then take its cube root, because that would be 8 to the 2 to the 1/3 power. Or you can take the cube root of 8 and then square it. That would be 8 to the 1/3 to the 2 power. All right. Well, what do we get if we do that? The first way, take 8 squared and then the cube root of it. You're taking the cube root of 64, and 64 is 4 times 4 times 4. So the cube root of 64 is 4. If we do it the other way, will we get the same answer? I sure hope so. The cube root of 8 is 2. Square that, we get 4. So yes, it doesn't matter which way you do it. Okay. So how about this one? The square root of 8 divided by 2 to the 1/2. Simplify this. I'll let you try that one for a few seconds. So who wants to boldly volunteer an answer to this question? What you get? 2? Other people get 2? All right. Does anyone get something besides 2? Maybe like the square root of 4 or something? That's actually also 2, right? And you can simplify this by converting all of the numbers to powers of 2, right? You can think of the cube root of 8, the square root of 8 as the square root of 2 cubed. That would be 2 to the 3/2. The denominator is 2 to the 1/2. When you're taking a quotient of powers and the base is the same, you just subtract the exponents. So it's 2 to the 3/2 minus 1/2. That's 2 to the 1. The answer is 2. All right. So if you got 2, good job. Now, I think we mentioned this already, but it's worth saying again. As long as the base is greater than 1, then the limit as x goes to infinity of a to the x is infinity, and the limit as x goes to negative infinity of a to the x is 0. If the base is in between 0 and 1, then the limit as x goes to infinity of a to the x is 0, and the limit as x goes to negative infinity of x, a to the x is infinity. And we saw this on the same graph earlier. Okay, and the reason for the distinction is that if a is in between 0 and 1, then taking it to a positive power is going to make it smaller. 1/2 to the 10th is small. If the base is in between 0 and 1 and you take it to a negative power, well, then you're first taking the reciprocal, which will make it bigger than 1, and then you're going to take it to a large positive power. Notice anytime you take the reciprocal of a number bigger than 1, you get something that's in between 0 and 1. And if you take the reciprocal of a number in between 0 and 1, you get something which is bigger than 1. And that's why you have this symmetry in the diagram across the y-axis. Okay. So, you can use these facts to get some basic kind of graphical fluency. If you need to graph 1/3 to the x, well, you could try to plot a bunch of points, or you could just say, all right, well, 1/3 to the x, that is the reflection of 3 to the x. And 3 to the x basically does one of these things, right? It goes to infinity on one side and it goes to negative infinity on the other, or 0 on the other side. So 1/3 to the x will have a basic shape kind of like this. Okay. So that's for properties of exponential functions. And there's one very special exponential that we want to focus on next. And we'll derive this exponential from the idea of compound interest. So how many of you have a savings account? Okay, I have a savings account too. Do you guys know what the interest on your savings account is? What did you say? Really small. Does anyone? I want to know the actual number if anyone knows. 0.4? Oh, I got you beat. I have 0.95. They used to have really high, well, comparatively high interest rates on savings accounts. But to be realistic would be to be depressing. So let's instead pretend that our interest account, or our savings account, gets 10% annual interest with interest compounded, let's say, once a year. Okay, now compounding of interest means that the interest you make gets thrown into the same bucket of money as the money you deposit. So that's your money to keep, and it can earn its own interest. All right, so how much money do you have after a year of saving $100 at 10% annual interest? Hopefully this is not too challenging of an arithmetic problem. Take $100, you put it in the bank. After 1 year, you get 10% back as interest. So what's your balance after 1 year? $110. There you go. Okay, what's your balance after 2 years? Well, you get your $110, that's yours, and then you get another 10% of that for interest. So what's that? $121. Now, they used to have these accounts called simple interest-bearing accounts as opposed to compound interest-bearing accounts. And in those, the interest would go into a separate column, and you couldn't earn interest on interest. So with the simple interest account, you would get $10 in the first year and another $10 in the second year. So you would only have $120. After T years, how much money will you have in this compound interest account? Well, you get 10% after each year. And adding 10% is the same as multiplying by what number? You're adding 10%. You're multiplying by what? You're multiplying by 0.1 to get the interest, but because you get to keep your principal, you multiply by 1.1. You get your principal plus the 10%. So you get 1 times your principal plus another 10% times your principal. So you get $100 times 1.1 to the t power. Okay. Does this make sense to everyone? It's going to get more complicated. So if you have a question, now would be the time to ask. Okay. Good. You've been warned. Now let's say that you have the same savings account. You put in $100. You still get the 10% annual interest, but the bank has now decided to compound it quarterly. So every 3 months, you get a little interest thrown into your bank account. The question again is, how much do you have after 1 year, after 2 years, and then after some general amount, t years? Well, after 1 year, how many times have we gotten interest? We've gotten 4 times. Okay. And here's an important semantic or important question relating to the actual real world of interest. Do you get that 10% 4 times each year? No, you actually get a fourth of the 10% 4 times a year. Because to give you 10% every 3 months would very much increase the amount of interest you got and basically be getting a much larger annual interest rate. So the 10% annually is split up into 4 compoundings. That means we get 2.5% every 3 months, 4 times a year. And so over the course of a year, we get that 2.5% added on 4 times. And if you do the math, or ask your calculator to do the math, you have $110.38. Okay? So the difference between getting your interest compounded once a year and 4 times a year is 38 cents. All right? That doesn't sound like a whole lot, but it's 38 cents on a principal of $100. So it's 0.38%. If you had $10,000 instead of $100, then the difference in your interest would be $38. And now we're talking real money, right? $38, that buys a lot of coffee. Right? So not 1.1 to the 4th power, that would be 40% annually compounded 4 times a year. We take the 10% and divide it by 4. Okay, after 2 years, how much would we have? You don't have to tell me this number. You can tell me this number. 1.025 to the 8th power, that's right. Okay, if you plug that in, you get $121 to the plus 84 cents. Okay, yes, we do get more money because of the extra compoundings, but notice also that the difference in the money that we get because of the extra compoundings is growing. We were 38 cents more after 1 year, but 84 cents more after 2 years. Not just 38, not even 76, but 84 cents more. Okay? And after T years, we would have $100 times 1.025 to the 4T power, because we had 4T compoundings, each of them getting us 2.5% interest. Okay? Still with me? All right, so my bank account does quarterly, but you might have one that compounds monthly. So at the end of every month, you get an interest statement. And again, you can ask the question, how much will you have after 1 year, 2 year, or T years? Well, we've already been through 2 of these examples, so maybe you can skip straight to the general. How much will you have after T years? $1.09 something? And how do you arrive at the 1.09 something? Right, take that 10% and divide it by 12. Okay, and what power are we going to raise it to? Well, if we get it 12 times a year for T years, we get it 12T times. Okay, and I'm starting to write it in a way so that you can see the general idea, how you might answer the question if the interest rate were not 10% annually, but 3% annually. Well, then you would just write 3% here instead of 10%. Or some number R percent annually, you could write it in right here, okay? And so on, right? So let's say now that we have a principal of P, whatever it is, we get interest rate R. It's compounded n times a year, whatever n is. And the question is, how much do we have after T years? Oh my God, look at all these letters. Well, we just have to substitute in the letters that we were using for numbers in this previous example. So instead of $100, we'll just write P. Instead of 10%, we'll write R. Instead of 12, we'll write N. And T will still be T. So the answer we'll get is P times 1 plus R over N to the NT power. This is the amount of money we would have in our account if it were compounded n times a year for T years. Okay. Looks nasty, but it's really just a generalization of what we've been doing in the previous 4 or 5 slides. Okay. So we started compounding once a year, and then we went to 4 times a year. We saw we got more money. If you were to compound it 12 times a year, you would get even more money. You might find a bank that will compound your interest weekly, maybe, or daily, right, 365 times a year, or hourly, wouldn't that be cool? Or minutely, or secondly, or millisecondly. And you can ask yourself, how much money am I eventually going to make? You know, is the amount of money that I will make on interest going to grow unboundedly as I increase the number of compoundings? Or is there some limit to the amount of interest I can make no matter how many compoundings I take? Okay, so how many think you can make an infinite amount of money just by compounding more and more and more? Okay, so I guess the rest of you will say that there must be some upper limit to the amount of money that I can make no matter how many times I compound it. Okay, we have a 1/2 to 0 decision. Okay, the question we are asking then is, what is the limit of this interest calculation as the number of compoundings goes to infinity? Right? If I compound every minute, every second, every half a second, every millisecond, every femtosecond, how much money can I make? That's a question about this limit as n gets ever and ever larger. Well, it turns out you can play with this expression a little bit, and you can write it as something which doesn't have a p or an r or a t in it. It's really the limit as n goes to infinity of 1 plus 1 over n to the n power. So think about this sequence of numbers. Let n be 2. Take 1 plus a half. That's 3 halves squared. Then take 1 plus a third to the cube, and 1 plus a fourth to the 4th power, and so on. As n gets larger and larger, what happens to 1 plus 1 over n? That just goes to 1, because 1 over n is going to 0, so 1 plus 1 over n is going to 1. And 1 to anything is just 1. So maybe this limit is 1. On the other hand, the power is going to infinity. If you take a number which is bigger than 1 and raise it to an ever larger power, you're going to get something which is infinite. Right? 2 to the 10, 2 to the million, 2 to the trillion, that's going to get infinitely large. Even 1.1 to the 10 to the 100 to the million, that's going to get infinitely large. So we have a dueling of monotonicities here. We've got 1 plus 1 over n, which is going to 1. 1 to the anything is 1. Yet we have a number bigger than 1 to a power which is ever larger. That seems like it should go to infinity. So where is it going to go? Well, it turns out that it does have a numerical value that's in between 1 and infinity. It's bigger than 1, but it's still finite. Okay? We call that number e. You seem happy. Well, that's why we call it. That's where it comes from. It's the limit as n goes to infinity, 1 plus 1 over n to the n power. And we can get better and better approximations to e by taking n to be larger and larger numbers. So if you want to write your continuously compounded interest formula, then you just say principal times e to the RT. Okay. So what is e? Well, here's a table by which we can get numbers closer and closer to e. Like we said, take 1 plus 1 over something to that thing power. 1 plus 1 over 1 to the 1 power is 2 to the 1, and that's 2. 1 plus 1 over 2 to the 2 power is 3 halves squared. That's 9 fourths. 1 plus 1 over 3 to the 3 power would be 4 thirds cubed. 4 thirds, that would be 64 27ths. 64 27ths is about 2.37. Okay. 1 plus 1 over 4 to the 4 power, oh, I got 10 here. 1 plus 1 over 10 to the 10th power, so 11 tenths to the 10th power is 2.59. Take a power of 100, 2.70. Take 1,000, 2.71. Take a million, and we get 2.71828. Okay, I don't know what the rest of them are. But it does appear that as this number gets ever and ever larger, this number is not going to infinity. This number is going to a limit which is positive, but finite. Okay, so that's our decimal approximation to e. If you plug it into your calculator or Wolfram Alpha, you'll get something like this, 2.718281828. And then you might get excited that maybe this block of 4 digits repeats it forever and ever, which would mean that this were a rational number. But alas, it goes on forever and ever without any pattern to it. E is an irrational number. And in fact, E is what we call a transcendental number. Now, that doesn't mean it meditates. It means that it's not only is it not a fraction, it's not like a square root or a cube root or any solution to a polynomial equation. Okay, so pi and e are two famous transcendental numbers. All right. So e was given its name by this guy, Euler. He did not name it after himself. He named it e for exponent, but it is a nice coincidence that it's also e for Euler. Euler was one of the most prolific mathematicians since Newton, basically. He was around in the 18th century. He was born in Switzerland, and he lived for a time in Prussia. Prussia is like the Berlin area of Germany now. And then moved up to, I think, St. Petersburg, which is in Russia now. So all of these countries claim Euler as one of their own. He's on a stamp in Switzerland, he's on a stamp in Germany, he's on a stamp in Russia. He used to be on the Swiss money, too, but now I think the Swiss are using the euro. Anyway, he was blind for most of his life, yet he still continued to write papers after papers after papers. Imagine doing your calculus homework blind. Sounds pretty hard, right? He's made hundreds of contributions to calculus, geometry, number theory. I don't think there's any field of mathematics that doesn't have a theorem called Euler's theorem in it. So, very, very amazing mathematician. He just celebrated his 300th birthday, which the Mathematical Association of America had a big to-do about a couple of years ago. Okay, so that's Euler. Now, we can ask this question related to e. What is the limit as h goes to 0 of e to the h minus 1 over h? Now, the fact that I'm using the letter h and that I'm taking a denominator whose quotient is, or I'm taking a quotient whose denominator is h, makes you think that this might be a question about a derivative. And indeed, when we come back from spring break, we will talk about the derivative of these exponential functions. But for now, let's just take a look at this single limit here. The limit is h goes to 0, e to the h minus 1 over h. Now, when you have these quotients, the first thing you want to check is, can I just plug in h equals 0? Well, can I do that? No, I can't, because the denominator will be 0, and we cannot divide by 0. So that's not going to work. What happens to the numerator? Well, as h goes to 0, e to the h goes to e to the 0, and e to the 0 is 1. Okay, so the numerator is also going to 0. This is where the magic happens, right? You have this amazing numerator and denominator both going to 0. Well, let me just sort of approximate what the limit should be. We know that the definition of e is the limit as n goes to infinity of 1 plus 1 over n to the nth power. That's by taking a large power and letting it go to infinity. Instead of taking a large number and letting it go to infinity, we can take a small number and let it go to 0. Instead of saying 1 plus 1/10th, 1/100th, 1,000th, 1/1,000,000th, we can say 1 plus 1/10th, 100th, 1,000th, 1,000,000th. And so this h is going to 0. Instead of taking it to a large power, we'll take it to the reciprocal of a small number power. All right, so this is just a change of the variable that gets us from this limit to this limit. And if this limit exists, we can take a small number h and just plug it in, and we should get a good approximation. For a small number h, e should be approximately 1 plus h to the 1 over h, 1 plus 100th to the 100 power, or 1 plus 1,000,000th to the 1,000,000th power. So if that's true, and I take e to the h, well, then I should get this to the h power. And this to the h power is exactly going to be 1 plus h. And if I subtract 1, then even the 1 will go away, and the numerator will then look like h. 1 plus h to the 1 over h to the h, well, these two are going to cancel away, leaving me 1 plus h. And then the 1 and the 1 are going to cancel away, leaving me just the h. And the h and the h will cancel away, and I'll be left with 1. All right, so by the definition of e as this limit, it looks as if the limit as h goes to 0 of e to the h minus 1 over h is exactly 1. Okay, you can check this numerically. It does work out. And as a matter of fact, there's another way to think about how you might define e. If you try this with numbers like 2, take the limit as h goes to 0 of 2 to the h minus 1 over h, and just evaluate it numerically. You'll get something that starts with 0.693, something, something, something. And if you try the same process with a base of 3, you'll get something which starts 1.09, something, something, something. And if you assume that this power function is continuous in the base, and it is, then you can use something like the intermediate value theorem to say that there's a base that's in between 2 and 3 for which this limit turns out to be 1. and that would be the number we call e. So you can alternatively define e to be the number which satisfies this equation. Okay. So that's it for the number e. Let's talk next about logarithmic functions, unless you have more questions about this. No? This one? Yeah? First thing you have to understand is that this limit and this limit are the same, because as n gets larger, 1 over n gets smaller. So instead of thinking about taking a large number n and then its reciprocal, I can just take a small number. Okay? And then you need to understand that by approximating, you can use the limit to approximate e as 1 plus h to the 1 over h for some small h. And then if you just take that to the h power, subtract 1, and divide by h, you get exactly 1. How does... Well, that's the one place I wouldn't say that. But if you take a large number n and then take its reciprocal, you get a small number, which we could call h. And contrary-wise, if you had a small number h, its reciprocal would be a large number, n. So we replace 1 over n with h. We replace n with 1 over h. And then as n gets larger, h gets smaller, and vice versa. Okay. You can even try sample n's and h's and evaluate what you're actually plugging into the calculator, and you'll see that you're plugging in the same expressions. Okay. So we have to get to the story about what is this thing on my belt. And so let's do that. And I'm not talking about the audio and the mic here. Okay. So these exponential functions, like lots of other functions, have inverse functions. Take the inverse of x squared, you get the square root of x. Take the inverse of x cubed, you get the cube root of x. You take the inverse of sine, you get the inverse sine of x. You take the inverse of a to the x, and you get log base a of x. So the definition of log base a of x is the number who stands for the power that you would put on a to get x. To say that y is log base a of x is precisely the same thing as saying x equals a to the y. And y is the power that you would put on a in order to get x. So a to the y is by definition of a of y. The answer would be x. And one of our exponential functions is special. When we use the base e, we call its corresponding logarithm ln, the natural logarithm. Okay, so to say that y equals the natural logarithm of x is the same as saying x equals e to the y. Okay, does that make sense? So we're defining new functions, but they're defined by their inverse properties with the exponential functions. Now, the thing that was so special about exponential functions was that they were constructed in a way that they would convert sums into products. E to the x times e to the x plus e to the y. E to the power x plus y is e to the x times e to the y. And that's true for any base a. Now, the inverse property is going to be true for the logarithms. The log of a product is the sum of logs. The log of a product is the sum of the logs, no matter what base you're taking. The log of a quotient is the difference of the logs, again, no matter what base you are taking. And the log of a power is that exponent multiplied by the log of the base. Right? These are the exact inverses of the properties that exponents convert sums into products, differences into quotients, and repeated powers into powers of a repeated exponent, or multiplied exponents. Okay? Their inverse properties are that logs change products back into sums, quotients back into differences, and powers into multiples. Okay? So, the fact that logarithms convert products into sums means that you can use addition to do multiplication. And so that brings me to this thing. So how many know what this is? You may have seen one of these in a museum. Right? This is a slide rule. Okay. How does the slide rule actually work? It's based on the property that the log of a product is the sum of the logs. There's a bunch of little lines on the slide rule, And the lines are not evenly spaced as if this were a ruler. They're spaced according to logarithms. So the further out you go, the more spread out these numbers are going to be. All right, so let's take two numbers. I was going to do this with a document camera, but I can't get it to light up right. So there's lots you can do with the slide rule. But for multiplication, what you use the two scales which are above and below this bottom line here. They're called the C scale and the D scale. Say I want to multiply 2 times 3. Never mind why I would do that with the slide rule, but just to demonstrate the concept, I'm going to align the 1 on the C scale with the 2 on the D scale. So the distance between the beginning and where it says 2 on the D scale, this distance is the natural log, well, a logarithm of 2. What I want to add to that is the natural log, or whatever logarithm this is, of 3. So I slide this along, hence slide rule, until I get to the number 3 on the C scale. Okay, so Marco, this is the D scale. What number is on the D scale just below 3 on the C scale? That should be a 6, right? The log of 2 plus the log of 3 would be the log of 2 times 3, and that's the log of 6. Okay? So we have used the slide rule to multiply 2 times 3. Now what if we want to multiply instead 25 times 33? Well, then I would put the 1 on the C scale between 2 and 3 on the D scale, so at 2.5. Right? Then I would slide the rule over till I got to 3.3, 3.3, 3.1, 3.2, 3.3. Okay, and now it gives me something around 8.4. You see what it says on the bottom? Okay, so 8.4, well, you didn't multiply 25 and 33. You multiplied 2.5 times 3.3. So you have to convert the powers of 10 right. You get 840 something. Okay, and that's why scientists use that scientific notation with the powers of 10, because it's easier to multiply when you just know the first couple of digits and then some power of 10. All right, so this looks quaint, right? And maybe even dangerously inaccurate, but this technology built bridges in the 20th century, so don't knock it. Okay, so you may use slide rules on your exams. How about that? Okay. Okay. Now you have to tell me where I put my clicker. Anyone see my clicker? All right, never mind. So how could we write, oh, it's over here on the podium. How could we write this number, 2 times the natural log of 4 minus the natural log of 3, as a single number? I forgot to tell you, the best part about this slide rule is it comes with its own scabbard. You can imagine an engineer walking around like this. So, what's that on your belt? It's my nerd sword. Yet another thing which is going out on the internet. Okay, write this as a single logarithm. 2 times the natural log of 4 minus the natural log of 3. Remember that the log of a quotient is the difference of the logs. The log of a multiple is the same as the power of that base. So 2 times the natural log of 4 is the same as the natural log of 4 squared. That 2 that's multiplying the log can also be thought of as an exponent. Okay? And the natural log of 4 squared minus the natural log of 3, that's the same thing as the natural log of 4 squared divided by 3. So you could say that this is the single logarithm of the number 16/3. Okay? Now, students will get this confused a lot and say that the difference of the logs is the same as the quotient of the logs. And that's not what we're saying about logarithms. The difference of the logs is the log of the quotient. Okay? The log of 4 squared divided by 3, not the log of 4 squared divided by the log of 3. Okay, so try this one yourself. Right, this is a single logarithm. Natural log of 3/4 plus 4 times natural log of 2. Mm-hmm. Sure. The log of base a of x to the r is r times log base a of x. So I'll back it up and show you. It's this one right here. Mm-hmm. Okay. Hey, young mathematicians, what do we have for this one here? A single logarithm. Okay. Yes? Natural log of 12. Very good. So how do we get natural log of 12? Well, this is the natural log of 3 minus the natural log of 4. The natural log of 4 can be written as the natural log of 2 squared. So that would be 2 times the natural log of 2. And then we have 4 times the natural log of 2. So you get the natural log of 3 plus 2 times the natural log of 2, which is the natural log of 3 times 4. So that's natural log of 12. I'm sure you'd like to see that written up. So on the part that I put online, I'll explain how you actually get that answer. All right, but the answer is natural log of 12. Okay? So let's look at pictures, because you know I like to draw pictures of graphs of functions. The idea that the logarithmic functions are inverses of the exponential functions means that you can construct the graphs of the logarithm functions from the graphs of the exponential functions. If you have a graph of a function f and you want the graph of its inverse, you're basically interchanging x's and y's, because inverse functions take the y back to its x, whatever was the x which produced that y. And graphically, when you're interchanging x and y, you've got stuff which is going out in this direction and y going up in this direction. Interchanging x and y means that they change their roles. And so what used to be horizontal is now vertical. And what used to be vertical is now horizontal. So the entire graph of the function of f gets flipped to get the graph of the inverse function. So what we're doing is that we're reflecting the graph of f along this diagonal line, which goes at a 45-degree angle. That is the line y equals x. And that will give us the graph of the inverse. So here's the graph of 2 to the x. And if we flip that graph across the diagonal, we get log base 2 of x. If we take the graph of 3 to the x and flip it, we get the graph of log base 3 of x. If we take the graph of 10 to the x and flip it, we get the graph of log base 10 of x. And if we take the graph of e to the x, then we get the graph of the natural log of x. Okay, each one of these graphs is a reflection of one of these graphs in the diagonal line y equals x. And so all the properties that were true about the exponential functions have corresponding properties about the logarithmic functions. For instance, the limit as x goes to infinity of a to the x is infinity, and therefore the limit as x goes to infinity of log base a of x is infinity. The limit as x goes to minus infinity of a to the x is 0, and therefore the limit as x goes to 0 of log base a of x is minus infinity. The x's and the y's are interchanging roles when you think about an inverse of a function. Okay, so that's the graphical picture. Now we've got lots of different logarithms floating around. I graphed you log base 2, log base 3, log base 10, and the natural log. And they all sort of have the same kind of shape, right? They all just go zoop, like that. And they all have the same limit at infinity, that is infinity. They all have the same limit at 0, that is negative infinity. So how can you compare logarithms to different bases? Well, it turns out there's a very simple way to do it. We have this, what we call the change of base formula. So if you have two numbers which are both positive and not 1, then the log base a of x is the log base b of x divided by the log base b of a. So what that says is that the function log base a of x is the same as the function log base b of x divided by a constant log base b of a. All right, dividing by a constant is basically the same as multiplying by a constant. So you can say that this function is a multiple of this function. And how would you derive such a formula like that? Well, you can just do it based on the properties of logarithms. If y is log base a of x, that's precisely the same thing as saying x equals a to the y. I'll take that equation and take the logarithm base b of the left-hand side and the right-hand side. Logarithm base b of x is the logarithm base b of a to the y. And using the fact that the log of a power is the exponent times the log of the base, I get y times log base b of a. So I can solve for y, and I get y is log base b of x divided by log base b of a. Okay? So if we have log to one base, and we want log to another base, then we can just compute by dividing by the log of one base to the other base. Right? So I could give you a question, How would you convert log base 10 if your calculator only had a natural logarithm, that is log base e, button to it? Or compute log base 2 using only log base 10. Right, well, log base 2 of the number 8 would be the log base 10 of the number 8 divided by the log base 10 of 2. And then if you just plug that into your calculator, you get 0.90309 and 0.30103, and the quotient is exactly 3. Now, does that surprise you that you got exactly 3 here? Is there another way to see that the log base 2 of 8 is 3? Yes, exactly. Go back to the definition of log base 2 of 8. That's the power you would put on 2 to get 8, and that is 3. Okay, so it does agree with something we figured out already. Okay, so not surprised. The log base 2 of 8 is already 3 just by using the definition. Now, so the upshot is that there are lots of different logarithms, but they're really all the same. They all have the same properties. And so you really just need to pick one and stick with it. So the engineers tend to prefer the log base 10. And I think it's because of that the whole slide rule thing. So they call that the common logarithm, and they abbreviate it just plain old log. Now, computer scientists often use logarithms to measure how much time or how much memory some algorithm takes. And a lot of their algorithms involve dividing their resources into half. You know, half of them look in the front and half of them look in the back, so you're looking for some string in a large file. And so they end up using a function called the binary logarithm. That's the log base 2. And they'll abbreviate it LG. I don't know how they say it. Maybe they just go. And mathematicians, because we like to take limits and we like to take derivatives, we prefer the logarithm to the base e, and we call it the natural logarithm. By the way, do you know why it's called the natural logarithm and abbreviated ln? Because it's in French. That's right, yeah. So you have to say everything backwards in French. It's logarithm naturel. And this is Euler's fault. Okay. So natural log is the log base e. So because we're in a math class, we're going to follow the mathematicians, and we'll be using the natural log for most of our calculations. And now, if you know some people who took some math courses, I think this is popular in Canada, they pronounce ln as ln. And I don't want you to do that. Natural log gets the natural pronunciation of its function. That is, we'll pronounce it log even though it's written ln. All right? So don't say ln. Thank you. Okay, so the big idea, exponentials turn sums into products. Logarithms turn products back to sums. And who doesn't want a nerd sword? Okay, have a great spring break. I'll see you in 12 days.